When life emerges, everything changes. 2.5 billion years ago, it changed the atmosphere of our planet and our signature in space. Organisms that are between 1 and 60 microns, they are pumping the CO2 from the atmosphere and releasing oxygen. And they changed everything.
Hi everybody, my name is Doug Barr and it's my pleasure to welcome you all to the St. Helena Forum for Innovation and Creativity. The Forum, as most of you know, is an educational nonprofit with a mission to entertain, inform, and inspire by presenting a broad mix of humanities-based programming. Today, we will be discussing two simple questions, neither of which has a simple answer. How did life begin, and are we alone in the universe? To help guide us, we've invited Dr. Nathalie Cabrol, who has spent most of her career pursuing answers to those very questions. Dr. Cabrol is a French American astrobiologist specializing in planetary science. Born near Paris, Dr. Cabrol attended Nanterre University as an undergraduate and the Sorbonne for her master's and PhD. Cabrol studies ancient lakes on Mars and has undertaken high-altitude scientific expeditions in the Central Andes of Chile as the principal investigator of the High Lakes projects funded by the NASA Astrobiology Institute. There with her team, she's documented life's adaptation to extreme environments, the effects of rapid climate change on lake ecosystems and habitats, its geobiological signatures, and relevance to planetary exploration. Her lake exploration included searching for microbes called extremophiles that have the ability to survive in harsh environments. Dr. Cabrol found an abundance of life, including new species and a massive field of fossilized microbial mats called stromatolites. Cabrol holds the women's world record for free diving and scuba diving in high altitudes. Nathalie was the principal investigator of the SETI Institute NAI team, which was selected to develop new biosignature detection and exploration strategies for the Mars 2020 mission. Appointed in 2015, she is the current head of the SETI Institute's Carl Sagan Center for the Study of Life in the Universe. Nathalie's work has been featured in the New York Times, on the Discovery Channel, Nova, BBC, National Geographic, Scientific American, and Popular Science. Nathalie has also written over 600 peer-reviewed publications and has published 5 books on planetary science, including her latest and soon-to-be-released The Secret Life of the Universe, an astrobiologist's search for the origins and frontiers of life, which we will be talking about in detail in today's interview. And so with that, everyone, please join me in welcoming Dr. Nathalie Cabrol. Hi, Nathalie. Thank you again for joining us today at the St. Helena Forum. It's great to have you with us, and we have a great deal to talk about today, and so I'll suggest that we just jump right into it, if that's okay with you.
All right, no problem. Happy to.
Okay, great. Well, it seems like we are living through sort of an extraordinary time for discovery in astronomy and cosmology, with the new images coming back from JWST of stars being born, and the recently launched Euclid mission, and the soon to be launched, we hope, Nancy Grace Roman Space Telescope. All of that combined, we're learning a great deal about our place in the cosmos, where do we come from and where we may be headed. Obviously, very big questions. You also are asking very big questions as an astrobiologist, but they may be even a little more relevant to us as humans, because you're asking, how did life begin? And where did life begin? And when did life begin? And importantly, are we alone in this universe? So what you're studying is incredibly interesting and exciting, but can you tell us how it is that all of these telescopes and the information and data coming from them helps you answer your big questions, and how do they help use your information to help them answer their questions?
Yeah, it's a iteration process, and astrobiology is asking the big questions. Certainly, the big telescopes right now are helping look at the universe in a very different way. Just the very first deep field from just James WST was remarkable. And we keep discovering. There is an article yesterday, I think, calling these little ruby things, we don't know what they are, at the very, very edge of whatever we can observe. But it's not only the telescopes, it's only the planetary missions, and it's also what we are discovering of our own planet. The baseline is that right now there is a revolution in our knowledge of planetary environment, habitability, the questions of life, discovering that there is a lot more to habitability than the habitable zone, for instance. That, well, we still have to find places on Earth where life doesn't exist. Of all the questions of astrobiology, the big ones that you've mentioned, and you forgot one, and that's very symptomatic, actually, because the third one, to me, is probably not necessarily the most important, but it is so hugely important right now at this point in time, because the three questions are, how does life originate? Okay, so this one is a big question. This is what you said. The second one is, are we alone? So in this big universe of ours, are we the only one to be able to just witness the beauty that surrounds us? But then the third one is, what is the future of life on Earth and beyond? And this is where, to me, this become an incredible quest, because not only we are looking outward to understand all of those questions, but then astrobiology and the search for life in the universe serves as a mirror to look at us and understand who we are and where we are heading. So big questions and lots of data. I wouldn't say responses yet.
It's really obviously an exciting time for you and for everybody in your field, and it is for the rest of us who are sort of paying attention to what's going on with this. It's astonishing in its beauty and the scale of all of what's going on. So it's a great time, I think, to be interested in what's happening in your world. Let me back up just a little bit and ask you, how did you find this interest in the first place? What was your passion as a kid or as a college student in astronomy or biology, or how did you get into this?
Well, truth is, I don't know, because it's something I was born with. If I had to trust my mom, she said that pretty much the first thing I said, pointing to the sky. So I was born with that in me, and never questioned that. And interestingly enough, growing up, I wasn't good at math and physics. I got my first degrees in literature,
Hmm.
of all things, and philosophy from the Sorbonne University. But then I went to environmental sciences and started digging into climatology, hydrology, etc. So the first planet that I actually studied was ours, and still wanted to be an astronomer. But at the time, astronomy was math and physics. But then, learning all I could about environments and habitability, which we weren't talking about, but this is what I was studying without knowing it. Then planetary sciences came about, and it was just the right time for me to engage in that field. And today, having those dual background is extremely useful, because I can bring together what we learned from the space mission and planetary mission to what I learned from extreme environments on Earth, for instance, and the background in climatology, as you know, may come handy these days.
I was a philosophy major as well, and I find that that's surprisingly handy. What can you tell us about Frank Drake and why meeting him was important to you?
Well, Frank was one of these encounters, in my life. I had a few like that. One of them was Hubert Reeves, who would have been at the time the equivalent of Carl Sagan in French-speaking countries, because I was born in France. But then in 1986, I met Carl. And so that was definitely an encounter that I still cherish. We had a good chat. And then Frank, obviously, is very important for the SETI Institute, and I'm the chief scientist now at the SETI Institute. So we are going to celebrate the 40th anniversary this year of the SETI Institute. So Frank has the central place, but he was also the person who interviewed me when I applied to come at the SETI Institute. So it was there too another encounter.
That's really great. Among other things, Carl Sagan is famous for the Sagan standard, which says extraordinary claims require extraordinary evidence. Is that still something that you sort of have in your mind whenever you're doing any of this research?
You have to if you're a scientist. You cannot just claim stuff and then walk away and say it's good enough to talk about it. In fact, it's especially relevant when you are looking for life. It is something so difficult to prove just because we don't have a definition for life. We have 123, and that was last week. So maybe we have more today, depending on what perspective you are approaching the question from. Um, and those are not definitions. They are actually more descriptions of what life is. We don't know what life is. We don't know what intelligence is. We don't know what consciousness is. And we're embarking in this incredible quest. And does it matter that we don't know or don't have a response to all those questions? I would say no, no, because what matters is that getting started, getting on the way. Because as you walk, then your perspective changes, and then you are getting more data and asking better questions, which is what science is about. But the Sagan standard, yes, it is very present in this ladder of life detection that astrobiology has, with 8 rungs of things that are, for lack of a better word, converging evidence. Right now, we have nothing that is unambiguous. And then, even if you have the 8 rungs, you check your boxes. On top of it, there is the Sagan standard. And then, since we don't have a definition for life, then it probably is going to remain a question mark unless we have a flying saucer landing in the middle of a lawn, or something very obvious.
Right, right. You just mentioned perspective. Can you talk a little bit about the pale blue dot and Carl Sagan turning the camera on Voyager 1's spacecraft back towards Earth from 6 billion miles in space to take a picture of it? That's perspective for certain. And I just read in the paper yesterday that they've fixed the Voyager 1, which was launched in 1977, and it's going to be working again. And now they're 15 billion miles away, and I'm wondering if they're going to turn that camera around and give us a new perspective. In any
Well, they
case,
are trying, to do as little science as possible. They are just keeping it talking, and it's talking again. So everything is well. But the pale blue dot, it happened at the time where we were changing perspective, and we have to put this into a broader perspective. No pun intended. We started having this overview effect we're talking about, which is to see our planet from space. And that first perspective, that was before the pale blue dot. That's during, the race to space. We started viewing our planet from space. But the astronauts started to put words around that. When we were done just sending rockets, I will always remember, it's that saying that we went all this way, talking about the moon, we went all this way to discover Earth. And so that's the first profound statement, by an astronaut. Today, they are all having this overview effect. They are all coming back with this urge of doing something to protect the planet. So there was that. And then, Carl, the pale blue dot is something even a little different, because when you are on the moon, you are in our neighborhood, right? The
yeah.
Earth is big. It takes only a couple of days at the time, to get there. But the pale blue dot, you are 4 billion kilometers away from the Earth. And then you look at this little dot that's a fraction of a pixel. And what happened there was not only this overview from very far about the fragility of our planet, but also all the statements in the Pale Blue Dot, the book, saying that, when you think about all of those we fought for just a little bit of time for a fraction of that dot so that they can be, dictators or of a fraction of that dot. There was all this wording from Sagan. That was the philosophical aspect of it. But there was something else. By that time, Sagan is actually doing what we're doing now, which is to look at the Earth like you would look at an exoplanet. And in February of 1990, which is when he actually, captured the pale blue dot, this was the philosophical message behind it. In October of the same year, he was actually a member of the Galileo mission. And Galileo was heading to the outer solar system and on its way to study Jupiter and Io, etc., but then needed to be accelerated. And so flew by a couple of times around the Earth. And at that point, because Sagan was Sagan and was never short of a good idea, just took all of the instruments with his team. And the instruments were not, aimed to do that. But still, he looked back at the Earth and tried to figure out if he could detect the presence of life looking remotely with a spacecraft down at our planet. And so you see 9 months apart, you have the philosophical message, and all of a sudden you have the roadmap, how to try and detect life on other planets. Mm-hmm. And for all I know, we are still using today some of what he used.
It's interesting. I remember that Sagan described his view in the pale blue dot as our planet looking like a mote of dust suspended in a sunbeam, which is quite poetic, and at the same time, it's very important in the sense of the perspective you get, but also maybe the sense of humility that you get from that distance.
Considering forget.
Yeah, there you go. So, considering the question of are we alone in the universe, you have said, and I'm going to quote you here: "As a scientist, I cannot wholly discount the hypothesis that we are, but it seems very unlikely and an awful waste of space." Can you just explain?
Well, Sagan said that. Sagan, right? I just added Carl's quote here because it seems so. And oftentimes this quote about statistical nonsense that's somewhere in the book too. I said, it's not only a awful waste of space, but it's also statistical nonsense. It's just not a matter of numbers only. I mean, this is ridiculous. The number there are as many planets as stars, in the universe, and you don't want to know how many more moons there are because we have about 260 or 80 moons, and some of them have a habitable environment. So now you add this to don't know how many trillion galaxies. So the numbers are staggering. But to me, it's not only a question of number, it's a question of combination of, the possibilities that they can produce something that we could understand to be life, or something so different that still be life, and we have no idea of.
Yeah.
So I am definitely not in favor of the rare earth hypothesis, as you can tell.
Very interesting. Thank you. In your book, The Secret Life of the Universe, which we're going to be talking about all through the day today, you talk about coevolution of life and environment as a key principle of astrobiology. Can you talk about the ways life and environment are interdependent, and also the role of adaptability in sustaining life?
Yeah, and I think that to me, Oftentimes, astrobiology is bottlenecking itself, trying to search for life, looking for environments as we know it. So that kind of confine our search to the type of life that we know. And at the same time, that makes sense because the stuff we are made of is very common, was produced very early and even earlier than we thought, thanks to James W.S.T. And there is water everywhere. So it's not completely, stupid to do what we're doing, but still, we're looking at potentially a small window into the vastness of space. And in terms of coevolution is what I think to be one of these universal processes that if life exists somewhere else, is going to happen. So, what do I mean by that? Well, let's assume for the Earth, like you are in the habitable zone, which means that for our biochemistry, the planet that we are looking at can sustain liquid water at the surface. It's not too cold or it's not too hot. And then let's imagine, because we are not completely sure of that yet, that we have an environment that's only physical, right? Physical and chemical. So this planet in this position in the habitable zone has some physical and chemical parameters that are going to be the constraint for the chemistry of life. All right? This is your environment.
Mm-hmm.
Now, the next thing we know is that when life emerges, everything changes. Of course, it can only emerge in some condition, which are the physical and chemical condition of that planet. But once it's there, well, let's see what happens. 2.5 billion years ago, it changed the atmosphere of our planet and our signature in space. And we are not talking about, big technologically advanced beings at that point. We are talking about organisms that are between 1 and 60 microns. And one by one and all together, they are pumping the CO2 from the atmosphere and releasing oxygen. And they changed everything. They absolutely changed everything. They changed the signature of the Earth in space. They also allowed for later on down the line, the evolution of multicellular organism, which was the path that was going to lead to us ultimately. They also, well, by the way, killed about 90% of the life that existed before, because the life before, the one that was breathing oxygen, well, it was chemoautotroph. It was not photosynthetic, and just took its energy from chemical, processes. So life can do a lot of things. And I mean, the atmosphere is something that's pretty well known, but I'm pretty sure that most people don't know that about a third of the minerals on Earth would not exist if life wasn't there. So, what life does, the environment gives, well, the condition for life. Life appears, change the environment. Environmental change, climatic change, life has to adapt, etc., etc. And this is intertwined. So when I look at this from the astrobiology standpoint, we are searching for life right now with astrobiology, trying to make sure that we can separate life from the environment. And I am pushing back on this because once you have the environment and then life, well, you don't have environment and life. You have a living planet, a living planet that is now the coevolution of both. And so with a level of complexity that is nothing like a rock without life on it. And when I say complexity, this is, words are so poor sometimes because, well, complexity and life can make things more simpler on the planet, or they can make life a lot more complicated. So the signature of complexity is not either simple or complex. So it is, it is absolutely fascinating. But the thing to remember is that um, a planet becomes habitable because it's located somewhere. Then life is going to change the environment of a planet. The environment is going to force life to evolve, and then is also changing the habitability of that planet.
Hmm.
Remember, because life is present on Earth, it changes the texture of rocks, it changes soils, it makes soils, it induces biogeochemical cycles, and then, it transforms the way water and energy flow on our planet. So it's not a simple thing. Coevolution is absolutely key. And I think that we, instead of saying we're searching for life, I think we should say we search for coevolution.
That's great. You also wrote that scientific exploration of our own planet has also intensified, like all of this work that's being done in space, by reaching into the Earth's most extreme environments. And I know that's something that you are particularly and intimately familiar with. Can you just give us a taste of the high altitude exploration research that you've done, and the High Lakes Project? And I'm going to mangle this, but Licancabore, is that the name of the volcanic lake that you
Milky
were?
Way, yeah,
There you go.
yeah, it's one of them. It's one of them. So the search for, the research in extreme environment is extremely valuable because, well, missions are pretty rare, although we are doing a good job, I think, at having a succession of missions right now. But when you cannot go directly to a mission, you try to find a place that looks a lot like the environment, the planetary environment you would like to explore. And depending on what you want to understand, you are going to one place or another. If I want to understand the signature of life in ice, I'm going to the poles or Iceland or anywhere where you have
Right.
permafrost and ice. In my case, I was really interested in understanding the habitability and potential for life on Mars very early on. So Mars and the Earth were very close in terms of environment, and we have this region of the earth that's called the Andes, the Altiplano, and the Atacama, which is an absolutely fantastic analog to this transition from the period when Mars was habitable and quite similar, although it was never like the Earth, but quite similar to the Earth, until the time it became this arid place that we know today, this red desert, rusty desert. And so the idea was to try and understand if any life could survive up there. So we took our gear and we explored this transition from the Atacama to the Andes. And this gradient is interesting. First, the Andes represent a beautiful primordial environment. You have volcanoes and evaporating lakes, hydrothermal springs, and the higher you go, the less oxygen you have. The atmosphere is thinner. The UV are getting harsher and shorter. So we are getting close, really, to what we saw on Mars. The only difference, in fact, is the abundance of oxygen in our atmosphere compared to that of Mars. But everything else is pretty close. So, we took our gear, climbed Licancabur, and I was interested in lakes. Why interested in lakes? Um, because they are a great place to have life started, especially when you have hydrothermal springs. But also, they are great places to keep the record of life that once were. And fossils are being made in lakes just because sediments are covering dead organism and they are preventing oxygen from destroying them. So we went up to 20,000 feet and had a lot of fun diving in those lakes that are pretty high. And the thing is that, as high as we went and as extreme as we were, life was still there. And it was abundant, not necessarily very diverse. And we learned about another way that life would create diversity, which is that because this region of the world is one very impacted by climate change, lakes are evaporating very, very, very quickly. So you have large lakes that year after year are being separated in different bodies of water because of the topography. And depending on where their spring is coming from, depending on the local, really local geology, they will evolve into completely different environment for life. And then you see evolution, you see adaptation, and you see extinction as well. So these are great lessons to understand the limit of habitability, and the great lessons for us was also, what type of life survive in this condition, and what does it take to detect those organisms. And this is the kind of things that we take, and then we're building instruments and experiments, and we send them to Mars or elsewhere.
It's fascinating what you do. It really is. In your book, you write, to finally answer whether life is a common or a rare occurrence in the universe, we must first understand how it emerged here on Earth. So besides that lake and others, where are the places that are currently being studied or that you hope to study here on the Earth? And where are people out looking?
Well, there is a great deal of work that's happening right now. There is an entire research domain about analogs. So we are putting a lot of effort. As I was mentioning earlier, people would go to the polar regions to understand, what's happening in ice. Others will go in Iceland. Some of my colleagues are diving under subglacial lakes to understand what might be happening in Iceland, for instance, to understand Europa or Enceladus. We're going to the bottom of the ocean near black smokers and white smokers, these big chimneys, that you find on the ocean floor, where the magma connects with the water of the ocean. And then you have these big rocky formation that are just, this chimney. You can see all of this chemistry happening. And there we're trying to understand how prebiotic chemistry, the stuff of life, the bricks of life, actually transition into life. And we still don't know when that happens.
There was a big piece in the New York Times just yesterday about the Homestake Mine in Lead, Colorado, and the extraordinary number of microbes that are down in there. I assume somebody's looking there. Um,
And you still can find them a kilometer under the rocks. I mean, it's not only about water. Well, it has to be about water for the metabolism of life as we know it. But you can be a kilometer, into the rock and still have water. You have energy because these rocks are still. They have, radioactivity. You don't need the sun. You can use that energy to metabolize. Life is incredible, so much so that it becomes really hard to pinpoint a place in what we still call the transition between the prebiotic chemistry to life. Does it make any sense to draw a line? It's really hard. And then you are entering, of course, a whole new set of questions, because we are only talking here about the chemical aspect of life, biochemistry, right? Other people are completely coming from a different place, and they are talking about physics and quantum physics for life. And to me, this is very promising because they are not talking about the origins of life, that they are talking about the nature of life. Life as a process, not life as a thing, and a process that's connected with the universal laws of the universe. And I like that very much because then we might not need a Sagan standard.
the how of the origin of life can be approached through various theories. I know one of them is that life results from a supernatural event, which is the foundation of most religions. God said, "Let there be light," and there was light. You go on to say, though, that science and religions are confronted with similar paradoxes. What do you mean by that?
Yeah, I do, and it's true. And for disclaimer, I am not a religious person, but I consider myself a very spiritual person. And again, just not to quote him again, but yeah, science is a great source of spirituality. But yeah, when I do have colleagues and friends who are religious, so science and religion, they are not opposed. They are just different ways of looking at the same thing and asking questions. But when they come to me and say, well, there is something that science cannot answer. What was before the Big Bang? And I agree, I don't have the answer to that. You can go to multiverses and you can still, there is a point where you do have to say what came before. But then I respond, nobody introduced me to God's parents. It's the same question. It's only a different way of perceiving things. And I have this tremendous privilege, being the chief scientist of the SETI Institute. We do have in our science board the director of the Vatican Observatory, and Guy Consolmagno is really, absolutely wonderful person. And we are having incredible discussions, the two of us, And I think we should, keep an open mind. And but the Big Bang is one of them. It's just my take on this is that science is a way for us to approach nature and understand nature by measuring it. And spirituality is left for everything we cannot measure.
Yeah, that makes a lot of sense. Uh, from a scientific perspective, you say it is not excluded at this time that there could be more than one origin of life. As a result, we often talk about the origins plural instead of the origin of life. Can you explain that and why it's important?
Well, it matters for a number of reasons. Down the road, I would say it matters for maybe the abundance of distribution of life in the universe. I think this is very important because, of course, we only have one data point, that's us, but it's still a data point. It worked. We're here to talk about those things, right? So, for one, the environment of the Earth was so nasty at the very beginning, during the Edean period between 4.5 to 4 billion years ago. You can imagine having mountain size or even bigger than that, Everest size, rocks and comets coming at the Earth and colliding with it. So we had this magma ocean at the surface of the Earth for the longest time. It took tens of millions of years for the Earth to start cooling down. So it was not always the pale blue dot. It was a pretty serious inferno when it started. And then, despite this, we know now we don't have a direct evidence, but we have indirect evidence. We found little crystal zircon that are extremely resilient, and some of them date back from 4.1, 4.2 billion years, and within them there is graphite. And when you study that, you discover that there is a disequilibrium in carbon 12 and carbon 13. Why is this important? Again, this is not the unambiguous evidence we would love to, but it is an interesting red flag. And the reason it's because, well, life in general is lazy. And it was lazy pretty early on, which means that when you are metabolizing and you want nutrients, you are going to go after the food that's the easiest to break. And carbon 12, the isotope, is easier to break than carbon 13. And usually, although it's not only a signature of life on Earth, you will see that in the organic matter that's left. So this is the kind of thing we discover in material that is 4.2 billion years old, maybe close to 4.3. What does that mean? Well, either it's not life at all and something else, but if it's life, it means that life was there by the time our surface had barely cooled down. And so that would make the emergence of life, almost a right away thing. So what happens? Well, unfortunately, at that time, so early, there were still big rocks circulating The planets were still forming and being destroyed. The solar system didn't look exactly what it looks like now. But you can imagine that if life took hold somewhere, and it's probably not in one place. If you had, comparable environments in different places, it's likely that it started to pop in different places. Well, there was probably as much destruction as creation at that time. And so I would say that it's very likely that life disappeared and reappeared and reemerged a number of times just because of that. That's the mechanical part of things. And now the other meaning of the plural for origins is that when you look at the various theories that we still have today about life, all obviously are talking about abiogenesis, meaning that life was born from, chemical association here on Earth, in environments on Earth. You have people who are saying, well, it emerged next to hydrothermal systems. And the oldest theory in that regard is that of the black smokers, the bottom of the ocean, actually sheltered from the surface. That's not a bad idea because then, asteroids and comets, you still can survive that if you are deep enough. And the white and black smokers are deep enough. But others say, yeah, I agree that it's around hydrothermal springs, but the ocean lacked something very important to create macromolecules, which is the cycle, the wet and dry cycle. So there you go. Now you have hydrothermal environments at the bottom of the ocean or hydrothermal environments at the surface on land. Other people say, wait, in fact, chemistry is a lot more stable in cold environment. And they can demonstrate to you that life could emerge in cold environment. Others say life doesn't need to be in the ocean, doesn't need to be near hydrothermal spring or in cold environment in ice. Just take clay. The structure of the clay mineral is enough to allow to even, get close to the point where macromolecule could reproduce. And what struck me when I looked at all of these theories, I went into a bit more depth, of course, for the book. All of this, when you are going through your research, etc. But I started reading more and getting more acquainted with every single one of them. And you say, but what if? What if all of them were possible? What if, every single one of these scenario actually happened? So the only thing that would go against this, maybe not, is that when we are going back in time, we are all coming from the same ancestor. So there is one tree of life on Earth. But that doesn't say that this tree of life was established, before or after the emergence of life, and maybe only one tree was left. So I like the idea of multiple environments for the beginning of life. For now, we are seeing only evidence for one unique ancestor for life on Earth. But obviously, you have colleagues who are pushing the envelope a little bit, always. And some of them are talking about the shadow biosphere. So there too, new horizons, the fact that there could be another type of life on Earth here and now that doesn't belong to the same tree of life as us, but because all of our tests are fine-tuned to discover the type of life we know, we cannot perceive something else as being alive or detect it. And I don't know if the shadow biosphere is real or not. I think it's an excellent theory to challenge us to find life as we don't know it.
That's interesting. The shadow biosphere, I haven't heard that before, and it's really fascinating that there could be such a thing. Can you just talk a little bit about Thea or Thea? I'm not sure about the pronunciation, the impact hypothesis,
Yeah.
and why it's really critical to Earth's evolution, as it turns out. And can you explain that to us?
Yeah, so as we said a little bit earlier, the early solar system was nothing like it is right now. Not going into migrations of planets, etc., but there is a lot of movement in the early solar system, and it's just like a big, derby where everybody's crashing into everybody. Orbits are being changed. Jupiter is heading towards the sun until Saturn pull it back where it is right now, thanks to us. But Mars is not too happy because in the process it lost a lot of material that would have made Mars as big as the Earth and Venus, and that would have changed everything for Mars. But in the process, around 4.5 or so billion years ago, there is a planetoid, so a small planet in formation, the size of Mars. So it's not a small thing. It's the size of the planet Mars. For some reason, ended up in a collision course with our planet, and it was a grazing collision course. And there are still different scenario, but what matters is that they collided. uh, the Theia, which is the name of that bolide that collided with the Earth, was destroyed completely, but at the same time, a good chunk of the Earth and the mantle of the Earth was also ejected into space and mixed with the debris of Theia. And the Earth still being there by gravity, the ring of debris started to accrete or assemble in orbit around the Earth. And so very quickly, now there are extreme scenarios. Some of them say that it took maybe 100 years or 1,000 years for the moon to become the moon, and for all of these debris to assemble. Some models seem to show that it could have been taking only a few days. So there are very, very big extremes here. But the point is that regardless of how long it took, now we had a moon in our sky. And what the moon did was to stabilize the Earth on its orbit, made the climate more stable as well. The tilt of the Earth would have wobbled a lot more if the moon was not here to stabilize it. There was also an exchange of energy between the two. And when you have two bodies running, turning, circling around each other, there is an acceleration. So the moon is actually getting away from us about 3 centimeters a year. But imagine, like 4.5 billion years ago, you have this massive world appearing in your sky only a few thousands of kilometers away, much, much closer than it is right now. And so we have new oceans on our planet. The crust finally cooled down. We had the first rain for millions of years. It rained on our planet. And now we have oceans, and the moon is here and pulling on those. And now you are having gigantic tides that were entering kilometers into the land, and humongous waves. You have to imagine that. That must have been something. We're always wary about the king's tides here, in the Bay of San Francisco, but that's nothing.
Can you just tell us what panspermia is and how that makes sense?
Well, Panspermia is the old world. To say that life could be distributed, dispersed, and convey from one place to another in the universe through by hitchhiking on comets, asteroids, etc., and through collision. You can bring the stuff of life on an environment that can be favorable to it, and then it will be, flourishing, and then you will have life. But the main issue with panspermia is really that it provides you with a means of distributing life. It doesn't explain anything about the origins of or the nature of life. It's just, push your question farther out in the universe. Now there is a more modern version of panspermia, and this is planetary exchange, and that's different. I mean, ultimately, it ends up being a little similar. What you have in planetary exchange, let's say you take the Earth and Mars. Mars was smaller than the Earth, cooled down faster, was planet ready faster than the Earth, had oceans before the Earth, maybe 200 million years before the Earth. So let's say that because the environment is similar, we are assuming that biochemistry emerged on Mars. Life is there. And then you have the early solar system, and you still have these big collisions. We are talking about those mountain sized rocks, right? And when they are impacting the Earth or Mars, well, they are ejecting lots of material and debris into space. So now what you have debris that's flying, some so fast that it escapes the gravity of the planet where they are coming from. And so they are roaming in space for a number of years. Actually, if you want to do the travel from Mars to the Earth, it's usually takes a few million years, between 500,000 and 2 million years. That's celestial mechanics. Um, and it's feasible from the Earth too. It takes a little longer, but what we have is because of collision, we know that the Earth and Mars exchanged material. So planetary exchange is that. Now, how life could have migrated from one to the other, that's the same idea as panspermia. You have a big impact in an area where you have life, bacteria, or the bricks of life, and then this is shot up into space, travels somehow protected within the rock that's, taking them on their merry way to somewhere else, and lands on another planet and there find a good environment and takes hold there. So we know for a fact that pieces of Mars have landed and keep landing on the Earth. We have the Martian meteorites. We know that. So that's the new, and this one demonstrated version of panspermia. Now, something that is also interesting with this whole concept of panspermia is that the more we look into interstellar or interplanetary space, and the more we explore small bodies like asteroids and comets, and the more we find that, well, the bricks of life and all the stuff that makes our DNA or RNA are already in there. So there is something about panspermia. It might not be the same romantic idea that people had at the beginning of the 20th century or at the end of 20th century when they were talking about it. But certainly planetary exchange and organic molecules are very abundant.
In fact, just to extend that, you say that today, and I'm quoting you here, we still do not know what exact environmental conditions led to life, but here is what we know for certain. The building blocks of life are everywhere, and they seem to be the easiest thing to form in a planetary nebula environment. This observation has led some to wonder, is life inevitable, evolving out of necessity rather than by accident, simply by following nature's physical and chemical laws? What's your opinion? Do you think life is inevitable?
Well, and that goes back to this thing we alluded to, which is looking and searching for life in the universe from two different perspectives. And they are not opposite perspective; they are complementary perspective. But right now, we are focusing on the origins of life, which is mostly environments and biochemistries, etc. And there is the nature of life, and the nature of life is different. It says that life is the inevitable result of thermodynamics. And some people are working on this right now. And to me, this opens incredible horizons and promises. Thermodynamics is a universal law. It's true everywhere in the universe. Then that takes your thought process to different places. Instead of looking for necessarily for water or etc., you are starting to ask question: does the thermodynamics that we see today, those laws, and the fact that it's acting in such a way, is this a generational thing in the universe at this point in time? In which case, the life that we're searching for is an emergence of that state of the universe at this point in time. And I find this absolutely mind boggling. I've been spending more time looking at this because these are universal markers. Entropy. This is what Jeremy England says. It's life is the inevitable result of thermodynamics because it's the best stuff to beat entropy. And so when you start with that, the next sentence could be, well, life has to be universal. And then what is life? What's the separation between life and non-living? And today we are really at the brink of, we are at the door, really at the door of starting to being able to answer those questions. I just cannot wait to see what Jeremy is doing with the next set of modeling that he's doing with his computing, because it is extremely, extremely promising.
There is so much going on with quantum computing and AI and trying to do robotics and create a sentient being, if that's possible to do. Just backing up a little bit, and cover something that you may have already covered enough, but I find it pretty interesting. Venus, as we take a look at our solar system's habitable zone, we find there are 3 planets: Venus, Mars, and the Earth. You suggest, though, that at one time all 3 might have harbored life. And can you expand on that a little bit?
No, I just said they were habitable.
Habitable.
That's not the same thing.
I got it. Okay. Would you say that
the 3 of them had oceans? We know that.
And so there's that similarity, so that there's that bit.
Yes.
Would you say that after examining several hypotheses, the answer to the question, did life ever develop on Venus, would be probably not? Or would you say the jury's still out?
I am pretty open-minded, but I think this is a tough nut to crack right there with Venus. So here's the thing. As I mentioned, there are 3 scenarios for Venus and the oceans on Venus. One of them said Venus never had any ocean. Another one said it had ocean and they lasted for 2 billion years. So plenty of time for life to develop, but then something happened. And another one is that Venus was, until pretty much what is the equivalent of the Cambrian revolution here, like 600 million years, ago, still had ocean. And then there was this global overturn, volcanic overturn, and then this runaway effect. And now we see the results with Venus. Others don't believe that at all. They say Venus was done from pretty much, as soon as the sun started to be on its main sequence. It was over because Venus was too close to the sun. So for Venus, it's really, really hard because when you think about right now conditions at the surface, they are unlivable. When people are talking about life on Venus, they are talking about life in the atmosphere of Venus, 60 kilometer up in the atmosphere, just because it happens so that there, the pressure and the temperature are the equivalent of what they are on average on the Earth. But there has to be more than that. It's just not a question of pressure and temperature. Then you have to think about, what an ecosystem, how an ecosystem could survive in the clouds. Granted that, okay, I'm willing to admit that anything can happen, but within certain limits. We know that there are plenty of bacteria and aerosols in the atmosphere of the Earth. I mean, you sample them all the time. But the thing is that they don't stay there. They don't make, a niche there. This is not an ecosystem niche. The atmosphere is something that is used to transport you from point A to point B. Most of the time, it's unwillingly, meaning that you have bacteria and other things that are at the surface of the ocean or the surface of on land, and then you have wind, volcanic eruption, and everything is picked up and brought up very high in the atmosphere. This is also how you find some microbes known in South America that you find in Antarctica and vice versa, for instance.
Mm-hmm.
They are being picked up, and this is also how the big cloud that you are seeing coming straight at Texas right now, that's leaving from Sahara, it's coming. It's a good thing, actually. People are really not happy, but this is a very good thing because this is going to help the Amazon by bringing lots of nutrients. And this has done that for thousands of years. But this is how it works. But life is not going to stay in the atmosphere because it's unstable. How do you build an ecosystem on clouds?
Yeah, makes no sense, right?
Right? And then if you say, okay, they have been picked up from the surface, like on the Earth, I don't think so. 93 times the atmospheric pressure, 450 degrees. Again, I'm willing to listen to many things, but I have my doubts.
Let's take a look if we can. Unfortunately, I'm skipping ahead a bit because we're running out of time, and I have about twice as many questions as we've already asked. So let me just jump ahead to Titan, Saturn's largest moon. And just in your book, you mentioned standing in a hallway with some other people who work for NASA, I think it was, and you were watching a probe land there. And this is how you described what you saw in the video that was coming out of the probe. You said, I was dumbfounded then like I am today. And every time I look at these images again, we could see hills, riverbeds, possibly a shoreline. To my eyes, it looked almost exactly like the landscape I fly over when I come back home from my travels abroad, as the plane is about to land in the Bay Area near San Francisco. The only difference was the apparent lack of vegetation and the hustle of humanity. I think we're all familiar with what that looks like landing in San Francisco. Is that really what it looks like on Titan?
It was so uncanny. It was so uncanny. And again, the only thing that was missing was all of a sudden the green oaks or the golden hills. Although the golden hills, we had this orange hue to the images. At the time, they were not processed, so it was black and white. But yes, because for the first time, I mean, it's not the first time it was not the first time we were seeing a dry riverbed. We had plenty on Mars. But what you had here were things looking like not only riverbeds, but also estuaries and lakes. None of them were active at the time where we landed the Huygens probe. The season was not when those lakes were actually active. But this is what happens on Titan. Titan is the closest, is actually, although we have 16 ocean worlds, including ours, in the solar system, only two have seas and lakes at the surface of these worlds. And this is the Earth and Titan. The only difference is that, well, you have liquid methane and ethane on Titan and not water, but it's the same type, like our hydrological cycle. It works the same way. You have evaporation, condensation, precipitation, and runoff. Exactly the same thing.
Fascinating.
And waves, big waves.
Good for surfing, I suppose. It was nearly 20 years ago that you made that comment about how it looked like San Francisco Bay. It sounds like there's been quite a bit of interest in Titan. Have there been other spacecraft that have gone there, either probes or flybys?
No, not at this point. And this is definitely somewhere we must go back, and we will. That's the good news. We have the Dragonfly mission that's we're still working on it, but it will land, by next decade. And I just cannot wait. You have this massive, it's not even a drone, it's a rotorcraft, the size of the Mars rover Perseverance and Curiosity. So this is this big thing with 8 blades. And the atmosphere of Titan is 1.5 times that of Earth. So it's going to be great. We are going to be able to hop from a dune field, and you have to imagine that the dunes on Titan, they are not made of sand, silica sand. They are made of organic molecules. I mean, imagine that. So we're going to land there and then go towards an impact crater where we are hoping that maybe in the ejecta we can find some traces of the water ocean that's underneath the surface, because there is also a water ocean underneath the surface.
And so does the Dragonfly project have some sort of a subsurface component that's going to go under the water?
No, unfortunately not, but it has enough remote sensing. to analyze the composition of what's at the surface.
Interesting. Really, really fascinating. Just when it looked like Europa, Enceladus, and Titan would be the most obvious candidates for life in our solar system, two more missions came out called Dawn and New Horizon, and they focused attention on dwarf planets, one particularly called Ceres, which came into view between Jupiter and Mars. Can you give us sort of a thumbnail description of Ceres and how it sizes up as a potential home for life?
Yeah, it's barely a few hundred kilometers in diameter. This is a bona fide asteroid. In fact, it was not even born there, born quote unquote, or formed there. This is one piece of rock that came from, the far end of the outer solar system and ended up there when everything was moving. But also is about a third of the entire mass of the asteroid belt. So it's a big presence in the asteroid belt between Jupiter and Mars. And the thing that was absolutely stunning is when the Dawn mission came and started to look at Ceres, it looked almost like somebody had left the lights on at the surface of this little world, because you have these really bright patches on top of a dark surface. And so what it is in fact, these are salt deposits, and they are we know their location, and that tells us that there is an ocean on Ceres. We don't know if it's still a global ocean or patches of salty pockets that are still, coming up to the surface, but the salt clearly indicate that there is some water and a lot of salt there. So that's the smallest world, in fact, we could imagine in the asteroid belt, of all places. But the one that really boggled our mind, and these were like 4 or 5 months apart. So a series that was in March 2015, and then the New Horizon mission, of course, with the flyby of Pluto on Bastille days, was just absolutely stunning. This is a world that we saw for the first time early in the 20th century that looked like, barely a dot with some albedo difference. And then Hubble started to show us something a little more interesting. We knew that there were differences, and that the atmosphere of Pluto is clearly dynamic. It can go from fairly thick to nothing at all. But then the flyby revealed a little world 6 billion kilometers away from the sun. The sun is about, you have as much light as in a full moon when you are on Pluto. And the sun is really not big at all. It's a big star, let's put it that way. Um, and now you have convection cells, and you have glaciers, and you have thalline deposits. So in some places, the whole surface is red because it's covered in organic molecules. And now you have cryovolcanoes. So what does that mean? Well, Pluto is so far away from the sun that the warmest stuff that's around is actually water ice. So that's basically what's coming out of volcanoes on Pluto, water ice. And then fissures and fractures and those convection cells. And well, now we know that there is still a residual ocean underneath the surface of Pluto. And when we are looking at the chemistry, etc., well, 6 billion years away from the sun, you have a little world that people thought would be as boring as a big snowball, is actually an incredible world where you have theoretically habitable environments for life. Doesn't mean that it's inhabited, but theoretically you have all the stuff you need.
Yeah, excellent. You say that every single day scientific discoveries show us that our place in the universe is not special, yet we have emerged from it after 4 billion years of evolution as living conscious beings. And then you go on to say, what's very different now is that the evidence is overwhelming that these worlds do exist. And for the past 30 years, we have become increasingly familiar with them, and even more so with their staggering abundance. Can you just give us, I know you want to talk about statistics, but can you just give us a sense of that abundance, of why that is a staggering abundance?
Yes, absolutely. So right now we have a little over 5,700 exoplanets that have been confirmed. We also have, to me, which is a probably the most interesting, is this zoo, this gallery of new worlds that we had no idea existed. The hot Jupiter and the Neptunian planets, the super Earth, and we have to think, we have to integrate those landscape into our thought process and start to model and see, how life could work in those worlds. We have discovered close to 2,000 planetary systems now, which means that it's at least a planet orbiting around a star, but most of the time you will have several of those. A few of them have 7 to 10 planets. One of the better known is the TRAPPIST system, with 7 planets the size of the Earth and Mars, except that if they were on our solar system, they would all be included in the orbit between Mercury and the Sun. So they are orbiting a very, very small star, a dwarf star. But so it's a cooler star than the Earth, but it's also using less energy, which means that it will last longer, many, many billion years longer than the sun will last. So we are discovering incredible worlds. In fact, you have 6 classes of stars. When we started on this journey to search for life elsewhere, we thought that we would be looking around sun-like stars, just because, it works around the stars like ours. Well, of the 6 classes of stars that we know, from the smallest to the biggest, we still have to find stars around the biggest one. In fact, we find planets around 5 classes of stars at this point in time. That doesn't mean that all of them will be habitable, but to make a long story short, we have as many planets as stars in our solar system. That's between 204 billion planet in our Milky Way. Of those, there might be as much as 300 millions that are habitable for life as we know it.
That's amazing. It's impossible to even grasp those numbers and what that looks like. In one of your book's final chapters, you say the building blocks that make us and all the planets were manufactured eons ago in distant stars now long dead. That alone gives us membership in a potentially large galactic family, one with which we all long to connect. This seems to imply to me that there is a continuum of existence for all things, including us, even if it's just as a mote of planetary dust floating in the vastness of space. Do you think that that's what that's saying?
What it says is that the process that has led to us, and we shouldn't see us as a finality in the universe, but the process that has led to us has started very, very early in the formation of the universe. In fact, when I wrote this chapter, I had to change it a little bit because a few weeks after I started writing it, which is the story of that book, I kept editing because discoveries are coming and coming and coming nonstop. We discovered organic molecules. 12 point something billion years, 12.9 billion years in the past. We discovered recently that atoms like carbon may have started to form much earlier than we thought, that carbon-based life could have been possible much earlier than we thought. So, it's hard, really, at this point in time. I would say we should be humble. We know what we know until we have to revise, and this is what science does. And that's the beauty of science, is that you allow yourself to say, okay, new evidence is telling me that I should amend what I thought was the best theory. And right now what we're seeing is that galaxies were formed a little earlier than we thought. I need to read this article telling that we're discovering simple thing, red thing, little dots very early, and that the early universe, is something a lot stranger than what we thought it would be. So what I can tell you, and this is where humility is that what's in this book, what we say, what we talk about today is the state of knowledge at this moment in time. And when I say at this moment in time, is really like right now, because I'm pretty sure that if I go and open my mail, there's going to be something telling me that we discovered something new, because we live in an incredible time where not only, knowledge is coming from space and planetary exploration, or even the exploration of extreme environment, as we said, but we need to start tying things that were not necessarily connected before. You were mentioning quantum physics, and I did too. This is where I have my eyes set on for the next decade. I think that there's going to be a revolution here. And the reason I'm saying this is that some people say, well, look at what's happening at very small scale. And for life, you have to look at that kind of scale.
Yeah.
That's Jeremy England, thermodynamics, etc. And then you have neuroscientists coming and say, that's interesting. It seems that our brain is communicating with the universe, at quantum level.
Yeah.
Yeah, and by the way, it also acting as a 11-dimension quantum computer. Don't ask me what that means. I have no clue. But this is what they are saying. And then you have others that are coming now and say, well, listen, it's all good and fine, but for the longest time, we thought about consciousness, as a functionality of the brain.
Right.
And others are coming and say, well,
yeah,
maybe it's not located in our brain at all. It's not even located in us at all. Maybe we're just having the right connection to tap into something that we call consciousness. So good luck with all of that. I think we are living in a fantastic time.
I do too. And I think you work in a business in which you ask the question, what if, over and over and over. It must just be an exciting way to go to work every morning. Unfortunately, we're nearly...
Well, it's not work. That's the thing.
It's not work. Exactly.
It's a passion.
What work should be is a passion. Exactly. And it'll never be work.
Yeah.
We're out of time. I'm going to have to just let you go. But before we do, I want to just read this little piece that you wrote, a few words about the environment. You wrote, "We live inside a closed ecosystem." You also say, "Where life and environment evolve in concert, and for the first time entirely and consciously, the fate of that environment and consequently of life on Earth are in the hands of one species." That's bad news, but it is also an opportunity in disguise, because it gives us much more power to fight than we give ourselves credit for if we only cared to care. Those sound like words to live by. Nathalie, what a pleasure this has been to meet you and get a chance to chat with you about all of this.
Thank you,
hopefully people will get out and find your book, The Secret Life of the Universe. It's just about to be released. It's just, I think in August, an astrobiologist.
August 15th, yeah. Well, 13th.
There you go. So look for that on the 13th, and I'm sure you'll be able to find it in all your bookstores. It has been such an honor to talk to you, and I can't tell you how much I appreciate you being with us today. I only wish we'd had a lot more time, because I have a lot more questions. So maybe we can convince you to come back another time in the future.
Maybe we'll do it again.
That would be a pleasure.
Because I'm sure we will be talking about completely different things, knowing the pace at which discoveries are being made.
Exactly right. Exactly.
Who knows?
Thank you, Nathalie. Talk to you soon.
Thank you, Doug.
Bye-bye.
Bye-bye.
Nathalie's book will be available starting tomorrow at bookstores everywhere and Amazon.com. To learn more about the forum, or to sign up for our mailing list or make a donation, please go to shforum.org. And finally, take a moment more, if you can, to enjoy Poet Laureate Ada Limon's reading of In Praise of Mystery, a poem for Europa, as we thank the following people for their generosity in making these presentations possible.
In Praise of Mystery, a poem for Europa. Arching under the night sky, inky with black expansiveness, we point to the planets we know. We pin quick wishes on stars. From Earth, we read the sky as if it is an unerring book of the universe, expert and evident. Still, there are mysteries below our sky, the whale song, the songbird singing its call in the bough of a wind-shaken tree. We are creatures of constant awe, curious at beauty, at leaf and blossom, at grief and pleasure, sun and shadow. And it is not darkness that unites us, not the cold distance of space, but the offering of water. Each drop of rain, each rivulet, each pulse, each vein. O second moon, we too are made of water, of vast and beckoning seas. We too are made of wonders, of great and ordinary loves, of small invisible worlds, of a need to call out through the dark.